I see it.
Sure. So let's just, I guess, dig into what is Pravega. At a high level, Pravega is a horizontally scaled storage system with the concept of a stream as the fundamental storage primitive. So a stream is kind of like a file opened in append mode, but writes can be sharded across regions of a routing key space. These regions we call segments. And writes can be ordered or unordered. So writes can specify a routing key to deterministically identify a segment, or writes can be unkeyed and assigned to segments at random. Very similar, I guess, to other horizontally scalable message systems. A stream kind of looks like this in Pravega. So on the vertical axis, we have the hashed routing key space. So like a float between 0 and 1, and then we have these like epochs in time on the horizontal axis. And you can kind of see, maybe we start out with 2 segments as we hit epoch T1. Traffic increases in 1 segment, so that segment splits into 2 segments. Same thing happens at T2 for the first segment, and then here at epoch T3, segments 2 and 5 sort of ramp down and merge, and then a stream is composed of what are your active segments, and your events sort of append, into each of these segments as according to how you're specifying routing. This is kind of what it looks like with a sort of simulated typical web traffic. As you see, with sort of moderate traffic, we have a lot of active segments. As traffic reduces, we see the segments merging according to an auto-scaling policy until at the lowest points of traffic, we have just 2 segments. And then as traffic ramps up again, the segments start splitting again to whatever the auto-scaling policy happens to be. You can auto-scale on sort of size of the segment or throughput. So what is Pravega really? This is maybe a more detailed look at under the covers. It's a tier 1 persistent log and stream cache. So this is down here, tier 1 storage, Apache Bookkeeper. We use Bookkeeper as a high throughput, distributed, durable write-ahead log. Now this write-ahead log, much like in typical journaled file systems, the log is used for recovery. So in this tier 1 storage, the data sort of lives in memory and it's acknowledged to the write-ahead log. And then the write-ahead log, should we lose this segment store that's holding this data in memory, the write-ahead log will be used to recover the state of the segment store. Additionally, there's like a tier 2 long-term storage. We have pluggable adapters to S3, file system, NFS, HDFS, and more can be added. So as things, I guess, pile up in the segment stores, they are asynchronously transferred to long-term storage. So basically fast acknowledgements on tier 1 with efficient and transparent migration to long-term storage in tier 2. So this might be an object store. What this kind of allows you, if you think about, I'm just writing to an object store, I have to finish writing the entire object before I can go read that object. Well, with kind of Pravega in the middle, we can start reading the objects as, kind of as they're being written to the object store. It's maybe one way to think about what we're enabling. This is a much more detailed diagram, sort of showing the split between API and abstractions at the top and implementation at the bottom. What we provide in terms of abstractions is the main abstraction of a stream. On top of stream segments, we've also built key value tables and a state synchronizer. And then I guess down here in the client, we have quite a quite a few different APIs and features in those APIs. The clients talk to a controller, which manages a lot of concerns in the cluster, and then the client also talks directly to the segment store. And it's a typical, I guess, source and sink type environment. If we're up here, we've got a lot of data sources using the system, and then data processors reading the system and possibly also producing more events. And so why did we build Pravega? Well, existing abstractions, whether like topics, queues, pub sub, they don't map really well to event streaming at scale. And some of these poorly suited abstractions, as they've evolved, enhancements have been sort of tacked on in an awkward fashion. And there's this conceptual mismatch negatively impacts both the computer programmer and the system administrator. If you've maybe ever tried to scale a Kafka cluster, you'll see that. Just a quick breakdown of features and capabilities across maybe competing systems. We all have transactions, we all have event streams. Long-term retention is something we kind of pioneered, but Pulsar has a long-term retention in the main branch now, and maybe this should be a half circle for Kafka. I think long-term retention is coming. Confluent has it. I think the open source driver is HDFS only, and the proprietary Confluent driver is S3. So Kafka's, I guess, catching up or keeping current. But in terms of being durable by default, Pulsar and Pravega are durable by default. I think I've seen discussion about Kafka changing its defaults. I think there's a cap out there. Auto scaling, that's sort of where we see a lot of our need. It can be very complicated to auto scale or to manually scale these other clusters. Ingestion of large data such as video. So this really speaks to our byte stream primitive. You can, a single segment stream is effectively a byte stream, or a remote append mode file. So we use that to do multimedia processing, digital signal processing on top of sort of multiple video streams. Kafka and Pulsar are doing this as well with packing buffers into messages, but we don't really, we have a pure byte stream. There aren't segmented buffers. We're efficient at high partition counts as well as at high producer counts. I'll show that in the next slide. Consistent state replication, that's using the the guarantees of our segments to do the state replication, and then key value tables is a recent addition to Pravega. So this is just a couple of graphs showing as we increase, we're keeping, in both of these graphs, we're keeping throughput the same. In one graph, we're increasing the number of writers as we keep the throughput the same. So as we introduce more writers, they take a share of the aggregate throughput. And we can see how Pravega can maintain a consistent throughput rate as we add more writers. As well, Pravega can contain consistent throughput rates as we add more partitions, or as we call them, segments. We can see the other systems degrade as these factors are increased. And due to this sort of two-level batching that Pravega does in its segment stores is kind of where multiple writers can come in and get batched into a segment container. Segment containers are a level of batching for the segments themselves, that several segments will be in a single segment container. And it's this two-level batching that allows Pravega to achieve these results. We can see in this graph, in these graphs. This is just a really quick example of the API. This code assumes a writer, a reader, and this routing key path config. This is kind of an example of an exactly once stream to stream copying routine. assuming the stream has JSON events, we begin a transaction in the writer. We tell the reader, we have the reader get the next event. If the event's not null, then we have something. If we configured this routine to extract routing keys from the message, we'll go ahead and extract a routing key, and then you can see here we either write the event to a random segment, or we write the event to a specific segment according to routing key. And otherwise, we've got this concept of checkpoints. If the event is null, it's likely we have a checkpoint. At the checkpoint, we commit the writer. The checkpoint is initiated by the reader. It allows us to commit the writer and achieve nearly exactly once semantics here. There may be like small failure conditions here with these exceptions. It could be, we could get to true exactly once with maybe some additional persistence on top of this, but just a really quick example, I guess, of a stream copying routine here. It kind of gives you the high level event stream API. And just some quick resources for Pravega. Our website's pravega.io. Our blog is at blog.pravega.io. We're on GitHub at github.com/pravega/pravega. That's the main server. We've got like 40 repositories for all kinds of other things. You can go to herokuapp.com and get an invite to our Slack. You can join our users mailing list, or check us out on Twitter at Pravega.io on Twitter. So that's kind of a, just a really high level introduction to what Pravega is. And then I guess I'll turn it over to Andrew to dig into what we've done with Pravega and Presto.
All right, thanks, Eric. Okay, yeah, hi everybody. My name is Andrew Robertson. So I'm going to just briefly talk about the connector work that we did to hook up Presto with Pravega. So just quickly, I'm going to probably skip Derek gave a pretty good Pravega overview. I'm just going to get a couple, just hit the kind of key points in the connector and kind of show you where all the moving pieces are there. Talk a little bit about what's next for the connector itself, and then just a simple demo and code walkthrough. It's not a ton of code, but I think it just illustrates the various couple ways that you can use the connector with Pravega. So again, Derek spoke to Pravega, so and it's just a time. Let's kind of skip over that. Oops, I was expecting all that to come out at the same time. So Pravega schema, right? Obviously, schema is used to get a list of schemas and tables in Presto. For us, we do that by listing scopes and streams in Pravega. So it's a Pravega scope is basically a namespace, and then you can have uniquely named streams within that scope or namespace, right? So we have mapped that onto a Presto schema, a table within a schema, right? So when we get asked for a list of schemas, we're listing scopes from Pravega. And when we are asked for a list of tables in a schema, we're listing streams within that scope. So obviously you need, from there on, you need to have like an actual schema of the data that's stored. We currently support Avro, Protobuf, JSON, and delimited like CSV. And we support a couple of ways to actually get the schema, right? So you can either look it up from something called Schema Registry, which I'll touch on in a second, or you can have sort of things defined locally in a file on the coordinator. So the actual, so Schema Registry, there's an actual Pravega product called Schema Registry. And it's a first-class Pravega project. It's general purpose, but as you might imagine, has a lot of integration with Pravega itself, right? So it gives you serializers and deserializers, has some client libraries that you can hook up to your Pravega client, and it'll manage your schemas for you, right? If that's what you want to do. So it'll take care of storing the schemas, managing them, validating them, and kind of versioning them and tracking evolution as you go on. You don't have to use that, but if it's configured for us, basically we're looking by convention for an object called a group in Schema Registry, and it's scope.stream. So we will look for something in Schema Registry called scope.stream. If it's there, we'll use the schema that's defined there. The next is you can have things in a local file. So just on the coordinator, it's one file per object, and basically you're either just inlining the event definition right there in JSON format, or just an example here, you can just point to like an arrow schema, right? So basically saying, you know, my schema is HR, the table name is I want it to show up in Presto, it's called employee, and object name is the stream on the Pravega side, right? So we'll look for HR.employee within Pravega and read from there, and we will use the schemas defined there. Presto table description supplier class for us is kind of the main driver of the metadata for Presto. This is where we do all the mapping, the looking up from Pravega for the scopes and streams, and looking up for schemas, right? So we just talked about either we're going to have a local file for our schema, or we're going to check schema registry, right? So that's kind of the order we do. If we find something locally, we'll use that schema. Else we'll look in the schema registry if it's configured, right? And then at that point, we're just mapping, you know, for example, like the fields in your Avro definition to Presto table definition. The other thing it supports too is being able to query multiple streams at once. Like a lot of times, you know, in Pravega, you may have a lot of streams that are kind of doing similar things, maybe from different kind of sources. So if you had streams that are same type, sensor 0 through sensor whatever, sensor n, you can set that up to query them all as a single table, and you know it does the caching of schemas and table definitions. Okay, so more interesting stuff. So defining splits, right? So basically, I mean, as all folks I'm sure are aware, right? The splits is how the workload kind of gets split up and spread amongst all the workers, right? So for us, we kind of have two stories. We have what we have now, and then what's coming, right? So our parallelization is basically at the segment level. So as Derek said, right, a stream is maybe made up of multiple segments, and that's what right now we're kind of locked into as far as concurrency. So if you have 16 segments, then we have 16 splits, each one reading a segment, right? And you can imagine that if a stream is very large or has a small number of segments, right, then we have kind of wasted power. And the issue for us there is we can't, and by we, I mean like a client application of Pravega, it's kind of hard to find an event boundary. So we can't break up a segment at some arbitrary place in a stream, right? We don't actually have that information. One thing we can use is something called the stream cut, which is just notes of position within a stream across all the segments. So you can, at this point, if you have knowledge of a stream cut, you can use that to find these event boundaries. And now instead of one split per segment, right now we can have, you know, the number of segments times the number of stream cuts that you have. So what we have now is an out-of-band way to store the stream cut information. So this would be a client application, just when they're writing their normal stream, every once in a while, maybe they'll persist the stream cut. Maybe this is after some number of events. Maybe this is after some number of megabytes of data that they've written, right? And then we'll read this specially named stream and use that stream cut information to kind of split things up. So that's what we have now. It's not optimal, and it's not going to be the final solution. But stream cuts is the way that we're going to be able to actually split up work for us. So it's briefly on processing splits. So a split is going to end up with something called a segment range, and all this is basically is just a start and end offset for a specific segment in a stream. So some number of events contained within this raw segment range. We're reading raw event bytes. So if you see on below, we use this thing called the batch client API. So Derek talked about how Pravega, there's like a lot of ordering and time guarantees and all that stuff when you read it, right? Well, using the batch client API, we can actually read the segments just as events as raw byte buffers, right? So we give up all the time ordering and all those sort of ordering guarantees for the ability to query things in parallel, right? And ordering doesn't necessarily mean as much for us because you can, the query can order it how it wants. So we're basically just reading these raw byte buffers and turning them into some sort of readable events, and we're setting up all the normal sort of Presto conventions for extracting fields, right? So we end up with a list of field value providers where then Presto can ask us for a value for a field in a row. So actually getting raw bytes into a readable object or a constructed object depends on how data is written. So as I mentioned that there's schema registry support. If you use schema registry, if schema registry client libraries itself are going to serialize the data for you. It's going to put a little bit of encoding information inline in the events so that when you read it out, again, using this schema registry libraries, it can look up the schema, it'll cache the schema locally, and it'll construct your object and give it back to you, right? Or you can just have a schema registry unaware client and just write raw bytes. So we basically need to know which that is, otherwise the parsing will fail because they're just, to us, arbitrary encoding info in the events. So we're basically just either configuring a deserializer that uses schema registry, or we're creating our own, right? But the end result is using a deserializer to give us the object back. And then, right, so when we're actually doing it, right, our record cursor is just basically using the bash client read segment. Read segment is just giving us some iterator to the events in the segment, and it's as simple as just getting next byte buffer until you get to the result set. We're using one of those two ways of deserializing, and then we build our row decoders from there, and then we're able to give the fields back when asked. So that's what we have now. Future work is we're really going to focus on query performance. I think at this point we've just got something up and running, which works, right? But the next step is to make it work really well. First and foremost is to create, do a better job of creating splits, right? So we already kind of have an idea of how we can do it. We have a POC to do it, to get splits of an basically arbitrary user-defined size. We can break things up, right? So we can get rid of that out of band, persisting stream cuts to make it seamless to an end user. And then a user in their query can set a session property, a little slider of how big they want their splits, and we can make that happen. So like I said, there's not just using existing stream metadata within Pravega. We have a POC for it and it's coming. And then, following all that is getting it production ready, right? It's not production ready now, but we're taking it there. So all kind of help or comments or anything in the community, would be great and be much much appreciated. But yeah, that's where we're headed. So I did have, I don't know how we're doing on time. I just kind of wanted to, I already ran the demo. So just going to quickly show it. And I just kind of wanted to show a couple of code snippets. So I was going to go ahead and do that. I don't know if anybody has any questions in the meantime.
In terms of time, the next presenter, Costin, will take 10 minutes. So
10 minutes?
I think you have time. Yeah.
Okay. All right, cool. All right, well, let me go ahead and, if I can remember my password. Okay, so we have, the first thing I think to mention, right, so we have our GitHub and our connector is under the Pravega org. And the first thing I guess just to point out is that and maybe this actually feeds well into the next one, but our code is maybe obvious to some, but it's not in the mainline Git for Presto DB, right? So it's under our own org. So our code, excuse me, is just compiled and built separately, right? So that's what we have here. So this is just our code, and we pull in everything as dependencies. So that's a sort of first thing to note. And then we have a little getting started. So just underneath there, getting started, we have a little demo. it's basically, you just bring up the stack, right? And the stack being Pravega itself, right? So brings up bookkeeper, zookeeper, Pravega, Pravega schema registry, brings that all up. It brings up a Presto DB image with our connector loaded onto it. And then you can run the sample code and ingest some data. So I already built an image, right? So our connector is not on there. So I just pulled an image and loaded our connector and copied our configs into the image. So that's already built locally and running. We don't publish anything right now. So that's what you have to do. You have to build our connector code, load the tarball, the plugin onto an existing Presto image, and then start it up. So I mentioned I've already done this. The things are up and running. Just takes a minute or two. It builds and ingests the data. Nothing too exciting to actually see on the screen, other than I just write 1,000 events of a couple of different types, right? And basically just shows the schemas that's stored in schema registry. Again, schema is showed in schema registry, and you'll notice the last one doesn't show any schema, and I'll talk about it in a second. So nothing terribly exciting there. So in this little code, so there's basically three things it's showing, or 4 things it's showing, I guess. There's 3 different ways that we're writing data. So the first one is it's like our client is very tightly integrated with schema registry, right? So in this case, we're creating a schema registry, a serializer that uses schema registry, right? So we're adding our group. I mentioned our naming format is scope.stream. We're saying, okay, here's my configuration, which is basically just the IP address of the schema registry itself. I want you to take care of managing schemas for me. And then I create a serializer based on the actual object that I want to do, right? So this is a schema registry provided serializer, right? And then we're using that. The second case is we're serializing things ourselves, right? I mean, the client application, but we're managing our schemas in schema registry, but we're not doing it in an automatic way. So I'm still adding my schema registry group. I'm telling it it's JSON. And here I'm explicitly adding the schema, right? So in this case, we're writing, the events that's written to Pravega does not contain any sort of metadata or encoding info. And I just have some, just basic serializer that I've made myself, right? So that's externally managed. And then the third way is we're not using schema registry at all, right? So I just have that same simple serializer, and I'm not putting schema anywhere. And then also in this app is just gives a little supplier, right? I mean, as you can see, I wrote 1,000 events of each, and it's just creating some dummy data, right? And it's giving that to the Pravega writer to actually write. So on that last case, right, is this simple object called transaction. And this is one where the schema is not managed anywhere. And then this is where right, they've defined the schema file locally on the coordinator, right? So this demo, right? So my scope is demo, my stream is transactions. And then this is the field event, the table definition inline, right? And then this is loaded onto the image for the coordinator to find, and our metadata component to find. So those are the 3 ways, and then all we do is just give it to just a generic method to insert the data, right? So this is the actual writing to Pravega. This doesn't know about schema registry, it doesn't know about Presto or anything. Just creating your scope for you, creating your stream for you, and then you creating a writer with your object type, right? It's just getting the data from our little dummy suppliers there, right? So we're just inserting our dummy data, and we're writing events. So the first part is the routing key, right? So you can use a routing key, and this is what distributes your objects across the segments within a stream. That you may key off of some piece of data in your object or something. For us, this is all just dummy data, test data. So we're basically just, by doing this, we're just basically try to spread things around more or less evenly. I've set up this thing called scaling policy, which I'm saying I want a fixed number of segments. There's 10 segments. So we're just basically writing these 1,000 events evenly across the 10 segments. And then that's it, right? So this is completely unaware of schema registry or schema or Presto or anything like that. So now at this point, the data, like I said, I already ran this. The data is in Pravega. So I'm just going to open the CLI, right? I'll go through this quickly because I'm sure most folks are intimately aware. Right, so again, show schemas from Pravega. At this point, we're listing scopes from Pravega, right? And we have demo. Show tables. Right now, I'm listing streams within the Pravega scope called demo. So I'm describing inventory, right? Inventory was one of the ones that managed schema registry. So at this point, I'm pulling that from schema registry, right? And then right, transactions was the one that's locally defined, and you see that here. And then you can right just dummy data here, right? But you can run your query, and it'll give you results. And then I just wanted to show quickly. And that's not readable. Right, so you can see all this was just looking up groups just externally to schema registry. Right, you can see that there's more than this, but you can see how in my groups I have something called demo.sensor, demo.inventory, right? And then I can use the schema registry REST API, to actually drill down and get those schemas, right? So that's how it's kind of all working together. So yeah, that's all I had prepared to show. Just kind of want to open up for questions about this or anything Pravega.
I think this is
Okay.
very interesting. Thanks for the presentation. I had just a few sort of questions just to help clarify my understanding.
Yeah.
So the stream cut concept, is this essentially a way from the client in the client side to sort of inform whoever's ingesting the data that this is a logical boundary of data, or I guess ignoring Presto,
Yeah.
what is the concept of stream cut, I guess?
Yeah, so stream cut is very much what the client application, so the application that's using Pravega wants it to be, right? So maybe when you're writing data, maybe you're writing data hourly. So you're at 1 hour, you're persisting a stream cut, right? And then you can kind of use that stream cut and logically map it to something with meaning, right? So you can say, okay, I logged the stream cut at this position in the stream at 11 o'clock in the morning on October 5th, right? And that where your data from October 5th at 11 a.m., right? It starts there. So it's really it's really up to the client, right? There's is what gives it meaning. So it's up to you how you want to use it in your application.
Gotcha.
Yeah, or in the stream to stream copying code sample I showed, the stream cuts would occur at the checkpoint times. So in the reader client I showed, by default checkpoints happen every 30 seconds. With an interval-based checkpoint, you're basically getting random offsets inside each segment. If we're talking Kafka terms, a stream cut would be the total collection of all topic partitions and offsets within those partitions for whatever your current position is, or for prior positions you've recorded.
Got it. And it sounds like typically a stream cut at worst would happen whenever a checkpoint happens, but it could potentially happen more frequently as well.
Yeah, correct. And yeah, checkpoints can be manually initiated as well. Or
where's the
Then
checkpoint?
go for it.
Sorry, I was going to ask, where's the checkpoint persisted?
in readers, you have a reader group, so much like a consumer group. The reader groups are backed by a state synchronizer metadata stream. And so readers will coordinate over this state synchronizer to initiate these checkpoints. Every checkpoint will be recorded, to the reader group metadata stream. It's so you can go there. Those streams are kind of pruned or truncated automatically, but you can find most recent checkpoints and prior checkpoints in those metadata streams. You can also take the stream cuts and save them off at your own locations. We don't. The stream cuts are a little bit obfuscated behind a base 64 string, but if you decode it and look in there, you'll see segment numbers and offsets. And we need to improve our stream cut handling to target, Druid or other systems where they want to natively know, each segment number and each offset number.
Thanks.
And then it sounds like the proposed enhancement that you had mentioned to automate the split size, just to clarify my understanding around that, it sounds like that would be, you would not be relying on the client side stream cut. Instead, you would be sort of automatically grouping together a bunch of these stream cuts until they hit a target size. And this would be called a split, just so that a system like Presto, you're giving information to the client to target a system like Presto so that they can efficiently,
Yeah, So exactly. So I mean, what Derek just said at the end, right? So actually being able to get start offsets within a segment, right, is the key. Because right now, there's no way to find an event boundary for us, right? So there's this concept called watermarking in Pravega, which basically is just internally, more or less taking a stream cut internally. And this is to help, when readers are, there's multiple readers in a reader group reading that data out. It's basically a way to let that all readers have passed a certain point within a stream, and that anything before that has been processed, right? So we can use that. It's internal to Pravega, so we can use that stream, and that gives us stream cuts, right? So we can use that in order to more or less get our arbitrary size of a split. But really, what we're after is just being able to find those event boundaries. So that's our first kind of proposed way, is to use some internal metadata from this watermark concept.
Maybe just one clarifying point. Offsets in Kafka are the message boundaries. Offsets in Pravega are bytes or byte offsets. Everything in Pravega is a byte stream. Yeah. Events, when you're writing events, we do put a tiny little length header, but that's about all we add to your data. And so I guess, maybe to Andrew's point as well, in order to improve some of this, we could maybe look at keeping event boundary indexes or so on.
Sounds good. Any other questions? I had one other question, which is the available serialization formats. It sounds like what they all have in common is they don't store, sort of like putting out the limitation of streaming storage in general, but the commonality between all of them is that they don't hold statistics, or sort of like file statistics. So I remember Avro and JSON, and I forget some of the others, but essentially the idea is in theory, any type of format where it could be represented as a list and doesn't have summary statistics, could be a suitable format in the future.
Yeah, so we can, Right, well, so I mean, the first thing maybe I should say, maybe not exactly to your question is, so I just wanted to clear up, so Pravega, you can store anything you want, right? So Pravega proper, you can store anything, right? It's not limited to Avro, JSON, protobuf, or the strings, right? So that's just us. The reason why the connector starts with that is just because that's what Schema Registry sort of supports natively, right? So it has serializers and deserializers for things like that. So that's why, that's how we ended up where we are, but we could support lots of types as long as we could be able to pull in the schema, and it's obviously easier with these formats.
Gotcha.
Yeah, but Pravega, there's no limitations in Pravega. I mean, Pravega, it's store whatever you want in there, right? It's just more on the connector side.
Any other questions? All right, thanks a lot, Andrew and Derek, and everyone at the Pravega team. It was very it was very interesting to learn about Pravega, and definitely, you know, like to hear more about the Pravega connector, and you know, like see more usage from that.
Yeah, thanks everyone for your time.